Giddy up. We're still talking about magnetic fields, and in this section we're going to determine the direction of the force when you have a wire going through a magnetic field, which way that wire is going to be pulled, and then also maybe you don't have a wire, maybe you've got a subatomic particle and it's flying through a magnetic field. What direction is that force going to be? And this is kind of a fun one because you get to use the third right-hand rule and you get to do funny things with your hand that makes other people think you're crazy. Now, let's say that we have a horseshoe magnet and it's got a magnetic field that you know goes from north to south. And let's say that we've got a wire with carrying a current right towards you coming out of the page. You should be able to predict which way this wire is going to be pulled, up, down, left, right, whatever. So to do that, take your right hand and we are going to say that you're always going to take your fingers and you're going to point them in the direction that the magnetic field goes. And if you remember, we will designate the magnetic field with a capital B, which kind of makes me think of bagnetic field, which kind of makes me laugh. No one else in the world does that, though. Your thumb is going to be the direction of the current. And that's conventional current. We're drawing it wrong because that's the way positive stuff goes, even though positives don't flow, but that's the way the world does it. So if positive current's flowing this way, your thumb goes that same way. Now, this is the palm or the inside of your right hand. And if you have field going one way, your thumb 90 degrees to that, then 90 degrees to that, pretend there's a laser that shoots out of your palm like your Iron Man, and it blasts out that way. That is going to be the force. And that's going to be what we're going to call the magnetic force. So in this situation here, you should have your right hand pointing from north to south. You should have, that's going to be depending on which way you're facing, you're going to have your current coming out of the board right to you, and the palm of your hand is going to be facing the way that the force is. And in this case, if I'm looking at this, then that's going to make the force be up on this wire. So I'm going to draw that says force, magnetic force is up. Now, just a quick review on some terminology here. Let's say that you see an X. We're going to say that that is a magnetic, or as I like to say, bagnetic field into the page. Picture that, that's like an arrow, ching, that you see the crosshairs and it's going in. If you see a dot, that is a B field out of the page. And if you see this, that is current, or I, into the page. And if you see this, that's current out. Now, the equation that will help you work with all this is what I like to call FILB, where, as you probably have guessed, F is the force on your wire, I is your current, how many amps you have, L is how long your wire is. In meters, and B is the magnetic, or as I like to call it, bagnetic field strength. And that will be measured in Teslas. Oh yeah, times sine of theta, where theta is the angle between magnetic field lines and the current. Now, quick note, sine of 90 degrees, hopefully you know, is 1. the sine of 0 degrees is 0. So hopefully you can see that you get the maximum force when the angle is 90 degrees. Or in other words, the wire and your field lines are perpendicular. If they're going the same way, or they're going opposite ways, then you'll get no force. So now let's say that wires and fields is too boring for you, and you want to fire subatomic particles into fields, like you're making an old school television or an atom smasher or something crazy like that. So if you have, as you see in this drawing here, I'm going to call it figure 6.20. These X's are the magnetic or bagnetic field going into the page, and let's say we've got a proton, positive particle, flying into this. The same right-hand rule that works for wires with conventional or positive current works for positive particles. So let's say we've got this particle going into, or flying this way. I'm going to try and do this from your perspective. As it flies into, with the velocity, that way. Now as you're looking at this, your fingers should be going into the page with the magnetic field. Your thumb is the velocity, so that should be going to your right. And the force is coming from your palm, so that's going up. So right here, we're going to have a force that bends upwards. And that's going to cause it to curve up like this. Now it's going this way. And so now you should have your fingers still into the page, your thumb pointing up, now your palm points towards the center of the circle, which is to your left. So now we have a force going this way. Hopefully you see what's happening. It gets bent over here. So now the velocity is going this way. Fingers are in. Your thumb is going over to your right, and the force is now down from your palm. And you can certainly probably see what's happening. It's going to curve and go into a continual circle. Now the equation that tells you how much force is very much like field. It's called Fiquiv, or F equal to QVB times the sine of theta. You know F is force. The Q here is the charge. If it's a proton, it's just whatever the charge of one proton is. V is the velocity. Sort of like where you used current before. B, again, is the magnetic field strength. And theta, as you can guess before, is the angle in between the velocity and the magnetic field direction. If that angle is 90 degrees, it's a maximum. If that angle is 0 or 180 degrees, then you get no force. One special note, if you have negative particles, you reverse this right-hand rule. So if you have a negative particle going in the field, you can do a couple different things. You can use the right hand, use your fingers in direction of magnetic field and thumb as velocity, but instead of the force coming out of your palm, you pretend the force comes out the back of your hand. Or you can use a left-hand rule in the same way, where your thumb actually is the direction of the negative particle like an electron, fingers are the magnetic field, and just as before, your palm shows the way that the force goes.